Good morning, students. Can you hear me? Good morning. So I'll start.
Good morning, sir.
Yes, I'll start with the lecture. On Monday, I started with the second chapter. It is about the magnetic field in materials. Now, this is in contrast with chapter 1, which is the magnetic field produced by the current carrying wire. So now, in this chapter, we study the magnetic field produced in the materials. Then, in the last lecture, I had defined what is called as the atomic currents. In material, the circulating electrons in an atom constitute the current because the charge flows in a closed path. So that is called the atomic current. This atomic current produces the magnetic field, that is the magnetic moment. And from the magnetic moment, we had defined what is called as a magnetization. This magnetization is a physical quantity. Now, the given material, example, a piece of iron is not magnetized. It does not produce any magnetic field. But if you keep it in some external field, then what will happen is it behaves like a magnet. That means it gets magnetized. Now that the magnetization of that material is defined by what is called as a magnetization vector, vector capital M. Then we define about a magnetization density. Now this magnetization density also we have defined a magnetization current. Magnetization density and magnetization current are equivalent quantities in the material corresponding to those physical quantity in a current carrying wire. Now we'll use these facts and we'll find the magnetic field produced by the magnetic material. So when given material, you take a iron or a copper or aluminum, any magnetic material, as such, it does not produce the magnetic field. That means its magnetization is zero. Magnetization is zero because the magnetic moment cancels. The total magnetic moment of that material is zero, so it does not produce the magnetization. But if you keep it in the external field, then it will get magnetized. And when it gets magnetized, what is the magnetic field? Now here when we say magnetic field, it is a magnetic intensity, a magnetic induction, B. That's what we want to find out. Magnetic field produced by the magnetic material. Then again in the comparison with the electrostatic, we'll define the potentials. We have already defined in the first chapter what are called as the potentials. So there are two, magnetic scalar potential and magnetic vector potential. Then in comparison with the electrostatic, we'll define here what are called as the pole density. So first let us take up the magnetic field produced by magnetic material. Now what we do here is, see we take here this medium, this is a medium. See what is drawn here is the medium. Its volume is V naught. Volume of this medium is V naught. Then it contains the atomic currents like this. I have shown here with the circles with an arrow, and that produces the magnetic moment, and that magnetic moment produces the magnetization. And what we'll do here is first find the magnetic field at this point. See magnetic field at this point. Now this point is inside this material. It is called as a field point. So we'll find out what is the magnetic field produced at that point. Now, to find out that magnetic field produced at the point, we'll make use of this formula, that magnetic field induction B is the curl of vector A. Vector A is the magnetic vector potential. See, that vector A is the magnetic vector potential. So first we'll try to find out what is the magnetic vector potential. And once you know that, we'll take a curl of that and find out the magnetic induction. So first we have to find out what is the magnetic vector potential. So this one, magnetic vector potential. We'll use this formula from the first chapter. Mu naught by 4 pi vector m. Vector m is the magnetic moment. Now this R2 is a distance. R2 is a distance of that point from that atomic current R2. That is the distance. It is a cross product of vector R2 divided by R2 cube. So now we'll apply this formula. In this case, in the magnetic material. So first what we will do is, we will find out what is the magnetic vector potential, and once you know what is the vector potential, we will find out the magnetic induction B. So we have considered here the volume V0. See, we have considered the volume V0 of the material. Then we consider the element. See, we will consider the element here. This box what I have drawn here, this is a volume element. Volume element means volume tending to 0. Now why we are taking this volume element? Because in that given volume element, that all the magnetic moment of all the atoms will be equal and in the same direction. So we take that volume element. Now this volume element is at this position, x dash comma y dash comma z dash. So corresponding, the position vector is r dash. This is a corresponding position vector is r dash. So r dash position vector means we take some origin, then this position vector like this. This is r dash. It is r dash. So this is a position vector of that element. Then, so magnetization produced at this point. See, magnetization produced at this element is vector m. Position is x dash, y dash, z dash. By definition, what we have defined on Monday, total magnetic moment divided by volume. So this is a total magnetic moment of this volume element. So this volume element will contain the atomic currents. So each atomic current will give rise to a magnetic moment. So total magnetic moment divided by the volume of that element. This is the definition. Magnetization is total magnetic moment divided by volume. So now from here, when you simplify this, we get that magnetic moment of that element. So what is the resultant magnetic moment? See, this element may contains many atomic currents. See, many atomic current, because many electrons will be orbiting here inside. So total magnetic moment of this element. So if you use this formula, it is a magnetization. Into volume. So we got a magnetic moment, and this is required to write the magnetic vector potential. And from the magnetic vector potential, you will find out the magnetic field by finding curl of A. So let us find out the magnetic field at a point inside. So at this point, this is at a point. Now in this magnetic vector potential, this R2 is this distance. See, R2 is this distance. This R2 is this distance of the element to the point. Then of this point where you are finding the magnetic field, this is the position vector. Vector R. So if you use the vector law of triangle, then you get this R2 equal to R minus R dash. So the position vector of the element is R dash, position vector of this point is R, then this part R2 will be, if you use a vector law of addition, then R minus R dash. So R2 in this case will turn out to be R minus R dash. So now what we will do here is, see this, we are using this formula. So we write this. Now what is given? Integrand. See, this integrand is the this vector potential, magnetic vector potential of the element. Then magnetic vector potential of the full material is the integral. See, what is that is what we have written. Integral over the volume. Integrand is that magnetic vector potential of the element. So when you integrate, you will get a magnetic vector potential of the full volume V naught. And how we write it? See, what we have is mu naught by 4 pi. So this mu naught by 4 pi is there. Then this M, magnetic moment. So magnetic moment is this one. This and this. Magnetization into the volume. See, this quantity and this quantity, when it is multiplied, this part, when it is multiplied, then it corresponds to magnetic moment. Then this R2 is the distance of that point from the element. That is nothing but R minus R dash divided by R2 cube, that is magnitude R minus R dash cube. So that is how we have written. Then mu naught by 4 pi we take outside. So mu naught by 4 pi integral of V net, and this M and R minus R dash divided by R minus R modulus cube. So this is the equation 1. So from the magnetization we got the magnetic moment. From the magnetic moment we got this magnetic vector potential. Then we had seen in the first chapter that magnetic field is a curl of vector A. And I had mentioned that time in the first chapter that magnetic vector potential is used to calculate the magnetic induction. So magnetic induction is B and it is the curl of vector A. So A we have already found. So this is the A and this is the del cross, so curl. Then, so now what you find here is, you can take this del inside also, del cross inside. So you will find out triple product. This is the one quantity, this is another quantity, and this is another quantity. So we can find, so sorry, this is the another quantity. So three quantities, cross and cross is there. So triple cross product. So we make use of this identity. Delta cross F cross G, divergence of the vector F, it is a scalar quantity. Scalar multiplied by vector, it is allowed. It is a vector quantity. So now this is the identity from the first term from the mathematical physics, very first chapter. The simplified form of the cross product, del cross A cross B cross C, A cross B cross C, del cross F cross G here. So what is there is a del. So F will take vector M and G will take this quantity. This will be G. This quantity will be G and this quantity is F. So this is what we are going to find. Del cross F cross G. So del is there, then F is vector M and G is this quantity. And this is the expansion. This is the expansion for that. So we will see that later in the next part. Here we use this here, and this del dot M is 0. Divergence of magnetization is 0 because magnetization, this del is like a derivative and M is a constant quantity. Vector M is a constant. So the derivative of constant quantity is 0. Then you apply it here when you substitute F equal to M. So you substitute F equal to M. So this we have written first term. This we have written first term. Now what happens here is, now this is del dot G is a scalar quantity. So F you can write before vector F or after vector F because this quantity is a scalar quantity. So in this case I have written that F first. F is vector M and this del dot G, G here is R minus R dash divided by R minus R dash cube. This we have written. Then this del dot this part is 0 because del dot m equal to 0. This part is 0. Then this uh, this part, if you apply your theory, this will be also equal to 0. Then this part here is this one. F is m, then g is r minus r dash divided by r minus r dash cube. Then we write it like this. This is as it is. So we write it this way. Then you substitute this in this equation 2 which you have written on the previous slide. So this, you take the del cross inside. So mu naught by 4 pi is here. Then this del cross is taken inside. So del cross m cross r minus r dash by r minus r dash cube. So it is written here. And what I have done here is, I have opened this bracket, integral, these two terms, this and this separately. So integral of v naught of this first term, integral of that of this one. Then this in the first term, we had shown that in the first term, we had defined what is called a direct delta function. In the electrostatic, we had shown that the del dot divergence of this r minus r dash divided by modulus of r minus r dash equal to 4 pi times this delta r minus r dash. This is called as a direct delta function. This is a direct delta function. So this one 4 pi delta r minus r dash is nothing but del dash r minus r dash divided by r minus r dash cube. Now this we have proved it in the electrostatic in one of the chapter. Now that delta is called as a direct delta function. Then this 4 pi will cancel, this 4 pi cancels. Then this integral of direct delta function, again here what is there is dv, it is not written there, dv dash is there, that is equal to 1. So here it is not typed there, dv dash, so it is dv dash is there. So integral of this m is constant will come out, and integral of this direct delta function is equal to 1. So what you get is here is mu naught and m. Other quantity will become 1. So mu naught m. Then here mu naught we keep inside, and I am taking this 4 pi inside this 4 pi. This 4 pi is taken inside like this. Inside it is taken. Okay, here it is taken. Here it is taken. So mu naught is there. Mu naught is there. So this gradient of 1 by 4 pi integral of v naught m dot r minus r dash by r minus r dash cube. Now if you look at this, see if you look at this formula, this magnetization into the volume is a magnetic moment. So it is a magnetic moment. So it is a magnetic moment. See, this magnetization into volume is a magnetic moment. Then this R2 is R minus R dash. R2 cube is modulus R minus R2 cube. That is what is called a phi star. And phi star is nothing but magnetic scalar potential. See, magnetic, so this quantity, see, this quantity, this full quantity is a magnetic scalar potential. So magnetic scalar potential of that full material. So we have written this magnetic field as mu naught m. M is a magnetization minus mu naught gradient of phi star. So m is the magnetization of the material, and this phi star is the magnetic scalar potential of the material. So we have expressed this magnetic field as the magnetization, and see the magnetic field is proportional to the magnetization. See, this first term is proportional to magnetization because mu naught is constant. Then second term is proportional minus of gradient of the magnetic scalar potential. So this very important equation which we have derived and which is required in the later part. So here I have written it again. So this, the magnetic induction, so it is a magnetic induction. B is now will be called as a magnetic induction. M is a magnetization. Due to magnetization distribution of the matter may be expressed as sum of the two terms. Term proportional to the local magnetization. Term proportional to the local magnetization. Then a gradient of the scalar field. So this is a gradient. Now this is a scalar field. It is a potential. This is a scalar potential. It is the in the first section of the previous semester we call it as a field. So potential is a field. It is a scalar field because it takes different values at a different point. Now suppose the point. So suppose this point is somewhere outside. See, outside there is no magnetization. Outside there is no magnetization. Since there is no magnetization, this M is 0. So external point, there is a vacuum. So magnetization is 0. So if this quantity is 0, this quantity is 0, then the magnetic induction will be minus mu naught gradient of that magnetic scalar potential. So just gradient of the scalar function, and that this scalar potential, what do you call it, the magnetic scalar potential. It is nothing but integral, because what happened is this material will act like a dipole. So at a distance, and this we have written is compared to the electrostatic distance dipole field. Then furthermore, see this we have already seen. See this we have already seen. This equation we have already proved. Just now we have proved it. Then this 5 star I have written here. This 5 star I have written it actual formula here and written there. Okay, and that 5 star is nothing but this 5 star is nothing but this. We have already written it. Now what we'll do here is we'll try to express it in a little different form here. So let us consider this. We'll consider this. Del dash. Del dash means minus del. Del dash means minus del dot. So now dot. Now there are two physical quantities. This is one physical quantity. Other is this physical quantity. So del dash is nothing but a derivative. So derivative of A into B. So first quantity into derivative of second quantity. So, this first quantity is vector M and second quantity is 1 by modulus of R minus R dash. So del dash is like a derivative. So first quantity into derivative of second quantity. I will write here dot because this is a vector quantity and this is also vector quantity. Plus the second quantity 1 by modulus of R minus R dash into derivative of the first quantity. So what I have written here is derivative of the product. So first quantity into derivative of second quantity, then second quantity into derivative of the first quantity. And wherever required, you have to write here dot, because this is vector quantity, this vector quantity, I have written dot here. This vector, that's why I have written dot here. Then del dash is nothing but minus del. That's what I have written. Del dash. Del dash is minus del. That is del dash. Then this I have written as it is. Then this this gradient of 1 by modulus of R minus R dash. Again, we have proved in the previous semester that gradient of R raised to N. See, gradient of R raised to N. That expansion, N equal to in this case minus 1. See, the R here, this is the R quantity R. So, 1 by R. So, R raised to minus 1. So, N equal to minus 1. And if you use in that formula, what you get is, when you expand this, you get R minus R dash divided by modulus of R minus R dash R cube. The formula we have used, see this, there is a formula, you can just refer it in the semester 5, this, you will get it there. So, gradient of R raised to N. So, N here in this case is minus 1. So, R here is R minus R dash. Then this will be as it is. So, we get this. This is what we want. We want this. See, we want this quantity. We want this quantity. So, that's why we have done this. So, this quantity is equal to this quantity del dash dot M by R minus R dash. minus, see plus goes on the side minus this quantity 1 by modulus of r minus r delta dot vector m. So now we are going to use it. So this we have proved. This we have proved on the previous page. This we have proved. Then these expressions also I had written here. So now we'll write a scalar potential. It's scalar magnetic scalar potential. We make use of this formula. 1 upon 4 pi integral of V naught vector m dot r minus r dash by modulus of r minus r dash cube dv dash. Then this we use this part. We use it here. So we write it that what is there inside del dash dot m by r minus r dash minus 1 by r minus r dash del dash m. Then you open the bracket. So you take the integral inside. So you open this bracket, then open this bracket. You get this. We get this expression. Then for the first part, use a divergence theorem. In the divergence theorem, volume integral becomes the surface integral. The divergence becomes the function. Say, volume integral of divergence of the function is surface integral of the function. See, volume integral is a volume integral of divergence. Del dot means divergence is a surface integral function. So function is m, and this is r minus r dash. And here, since surface integral is ds dash, so we get this equation 2. Second part we are not touching it, we are leaving it as it is. So now I have written it here. This is what we found on the previous slide. This is a magnetic scalar potential. Magnetic scalar potential. Phi star 1 upon 4 pi integral of surface integral m by r minus r dash, then minus 1 by 4 pi volume integral del dash dot m divided by r minus r dash. Now what I have written here, this I have picked up from the semester 5. In semester 5, in electrostatic, there is only one type of potential called as a scalar potential. And that scalar potential was shown to be equal to this, where this rho was a surface density, this sigma is a surface density, and rho is a volume density. Now this part, you have to consider that electromagnetic theory 1 is a semester 5. This comes from semester 5. It comes from semester 5. In fact, it is there in the second chapter. This is there in the second chapter. This scalar electric. This is the electric. See, this is electrostatics. Electric scalar potential is equal to 1 upon 4 pi epsilon 0 integral S naught rho p ds dash by this, and this is a sigma p and this is rho p. Now here in electrostatic, this the it is due to polarization. See, because of the polarization, the material had polarized. Now we use it similar thing here. You compare this, and similar to this quantity rho p, we define rho m. See, corresponding to this rho p, we define rho m in magnetism. It is called the magnetic pole density. Magnetic pole density. And if you compare this part, it is, say, the r minus r dash is there, r minus r dash is the dv dash is there. It is equal to this quantity along with the minus sign. Along with the minus sign. Sorry, here it is, in fact it is plus here. Okay, there is a mistake here, it is a plus along with the minus sign. So rho m equal to minus del dash dot m. Then corresponding to this quantity, we have this one. We have this part. Other thing is same. ds dash is there, r minus r dash is here, r minus r dash here. So sigma p, we write it as sigma m and m dot n, and this is called as the surface density of the magnetic pole strength. So there it was called as the electric surface density, and the electric volume density. Here it is surface density of magnetic pole strength and magnetic pole density. Now here this is sigma is equal to m dot n. N is no unit. So unit for m is ampere per meter. Ampere per meter. So unit for sigma is ampere per meter. Then for magnetic pole density, the unit for this comes from the current density. Unit is ampere per meter square. So in comparison electrostatic, we have also defined here the pole density. So one is the magnetic pole density rho m, other is the surface density magnetic pole strength rho m, and this formula is minus del dash dot m, here m dot n cap. In fact, knowing the magnetization, if you know the magnetization of the material, so when you keep the material in the extramagnetic field, it will get magnetized. Magnetized means what? The total magnetic moment will not become equal to 0. It will get magnetized. Example, if you take an iron piece and keep in the extramagnetic field, it will get magnetized. Now, what is that pole density or a surface density? You can use this formula to calculate. Just find minus del dash dot m dot product of the magnet del and magnetization. So what happened? Del dash is minus del. So minus minus will become plus. So you find the dot product of del and m. What you will get is the magnetic pole density. If you find this dot product of magnetization and this unit vector normal to the surface area, that will give the surface density of the magnetic pole strength. Then we substitute here. Say this equation 2 we have written. We substitute this quantity here, and you get this equation. So that is in terms of the densities, we have the formula for the magnetic scalar potential. Then we have proved this. Today only we have proved. This morning we have proved it. Then you substitute for what you have in terms of pole density. So you substitute it here. Then mu naught m, you keep it as it is. Then this 1 upon 4 pi you take inside. So then here del you take inside. Del of 1 by r minus r dash is r minus r dash divided by r minus r dash cube. Again, this identity we already proved in the first term. Okay, this we have proved. We have proved this del of del of r raised to n, and I already mentioned by using this formula you get it like this. So this gradient you take inside, and that is written like this. Similarly, this gradient you take it inside here, and you write it like this. So this is how the magnetic induction can be written in terms of the pole density. So this is in terms of pole density. So this completes this chapter. Sorry, this completes this topic, not chapter. So I have taken what is called the magnetic field produced by magnetic material, and I have defined magnetic scalar potential and magnetic pole density. So next section I will take it tomorrow, and I will stop here and continue tomorrow. Thank you very much.